Welcome you all to the NPTEL course on Economic Operation and Control of Power System. And today we'll focus on the second part of optimization preliminaries, where we will focus more or less on linear programming approaches. During the previous class, we have seen how different functions can be optimized. They could be single variable, they could be multivariable, they could be constrained or unconstrained, and the function may be linear or it could be nonlinear. And Lagrangian multiplier optimization technique we have understood, and how this can be extended to power system engineering. And today we will focus on linear optimization, because there are a bit of challenges that if the function, objective function is linear, and then probably when you differentiate it, then the differentiation become a constant. All right. So there is no opportunity for you to go for furthermore differentiation because the function is linear. And optimizing linear functions become a challenge. So we'll understand how linear functions can be optimized with equality as well as inequality constraint and its process. Now, first of all, when I talk about linear programming problem, we'll try to understand a very simple example. If I'm interested to maximize the production of two different plants, or I have to minimize the cost of two power plants, so then we need to express those in the form of equations. So probably, let's say I have to maximize the production cost of two different plants with 3x1 plus 5x2 is one of my objective function, and with different constraints there could be equality or inequality constraints. So if I say one of the inequality constraint, which is 3x1 plus 2x2 less than or equal to 18 is one of my constraints, then we'll try to solve this problem to best of our capabilities. Now what we need to do, you can see that I have to optimize the function, which is maximize 3x1 plus 5x2, and then subject to different constraints, where I say x1 must be less than or equal to 4, x2 is less than or equal to 6, as well as 3x1 plus 2x2 must be less than or equal to 18, and both the variables cannot be negative. So x1 is greater than or equal to 0 and x2 is greater than or equal to 0. So as a whole, I'm supposed to maximize a function satisfying all the constraints will give me the best solutions. Now, moving to the next case. So what exactly happens when you draw these different points or different constraints? Now, first of all, this is my x2, which is x2 greater than or equal to 0, and this is a small typo, x1 greater than or equal to 0. Okay, these are the two lines, and then you have one more constraint, which is x1 less than or equal to 4, and then we can have x2 less than or equal to 6. So you come across this line, and you come across this line, and finally the equation, which is 3x1 plus 2x2, which is a linear equation, less than or equal to 18 will give me. All right. So from this, I am getting now the feasible region. I'm getting different points, 1, 2, 3, 4, 5 different points, and the area which is now feasible to me. So I have to find a point within that. Now we can also solve a few more examples, like maximize another function, which is z equal to x plus y. X is a variable, y is a variable, similar to x1 and x2, and you can have multiple constraints. And when you have multiple constraints like x plus y less than or equal to 40, 2x plus y less than or equal to 60, with different constraint, x is positive, y is positive, you have to draw different characteristics similar to the previous diagram as I have shown, so you can get the feasible region within which the optimization value now being carried out. Now, what is the approach of doing it? Now, there are two different methods. One is real procedural steps for linear programming, and someone also can solve graphically and get an idea actually what the optimized value are. So if you look into this to maximize the value z equal to 8x plus y, you can see, there are different characteristics. So I can consider one point. Let's say when I say the point x equal to 0, y equal to 0, I can get it. And I can take x equal to 0, y is extreme 40. Then I can another take point 20, 20 and then 30, 0. So I do get different values for my objective functions. And those points, I can now plot it, okay? So when I plot those points, when it is 0 and 0, I get this point, all right? And then 0 and 40, I get this point, and then I get this point. 30 and 0, I get this point, okay? And this is my 30 and 0, this is my 0 and 40, and this is my 0 and 0. And then finally I get another point which is 20 and 20, all right? And from the characteristic, if you see, I mean, the feasible region is going to be this one, right? Which is satisfying all the points. So once you know the feasible region, then you can get the maximum value of the function easily from the characteristics. Now, when you talk about a linear program, what is it? It is an objective function with multiple constraints, and the final objective function need to be minimized or maximized. So we do have different variables. It talks about minimize the function, which is C transpose X, all right? That means your equation can be represented in the form of C transpose X, subject to constraint X is less than or equal to B or X is greater than or equal to 0. That is how we have seen all the formulas of the previous linear optimization problems. Now, when I talk about the LP objective functions, this exercise, as you could see, we have seen that there are different points here. So this is objective functions, which has been plotted with my different variables and constraints. So this is known as actually contours of linear functions, am I right? And you can say the objective functions at different point. And finally, I can get a point, either this or this or this or this or this will give me one of the reasonable optimal solution to me, am I right? The best one. So now this characteristic, as you could see, if I push this characteristic up, okay, then probably the points can move further actually, and which can keep on increasing. So what I wanted to highlight here, if the objective function is known to me, if the constraints are known to me, even through graphical method, the best value or best solution can be identified within a feasible region satisfying all the points. So indirectly, I do have millions of points within this characteristic, okay? But because we also know the optimal points will lie on the boundaries, and hence by checking the boundary points, one can easily say which is my optimal solution or the value of x1 and x2 that leads to the maximum or minimum of the objective functions. So this is one way, but for complicated problems with millions of variables or hundreds of variables or tens of variables, this method is not going to work. This is true for 2 variables, which can be easily done. But if there are 5 variables, 10 variables, how do you solve it? So for that, we need to get into canonical forms with slack variables, and where different objective functions with different constraints can be lined up. So you could see now the variables are not 1 or 2, but there are actually x1, x2, x3, x4, x5. Everything can be placed in a vector form, and that need to be solved. So I request everyone to get into the linear optimization textbooks to understand more detail about it, but we are just touching upon to make sure when you get into an objective function which is linear, that need to be optimized, and you are not able to solve by differentiating easily, because if I take this function, linear function f of x, which is x plus 3, all right, so what is my f dash x? Is 1. So I'm gone. So I cannot really get into what is f double dash x equal to 0. So by differential methods, obtaining the optimal value of linear functions become a challenge, and hence we have to go for linear programming approach to handle and avoid the challenges that are being faced through differentiation. Okay, so either you can code graphical methods, or we can present them in a canonical form with slack variables to solve this issue. And these are all classical structures and the way it can be presented. Now there are basic feasible solutions. So either it could be x equal to b is one of my solution. I can say x equal to b as well as x greater than equal to 0 is one of my solution. I can also say x equal to b and x greater than 0 and xn equal to 0, both equality and inequality. Okay, first one is without any constraint, second one is a inequality constraint, third is a equality as well as inequality constraint. So different type of problem formulations can be handled in your linear programming optimization techniques. Now, what we can do for a complicated problem, like your a value is known to me from this diagram itself, from this representation of canonical form is lag variables. I can arrive to the point what is a, what is b, and then I can have different set of equations for x1, x2, x3, and then and x1, x2, x4, and x1, x2, x4 different variables. I can determine the inverse and its multiplication to b, c inverse b, and or a inverse actually b will give me a solution for the jet. Now, what I wanted to highlight here, the equation, if I get into the originality, let us focus here. From this equation, you can easily understand what is the value of A. So, normally what we write an equation which is of linearity, so Ax equal to B. So, all those variables x can be stacked into x1, x2, x3, x4, x5 with a coefficient which has been represented by matrix A, and the right hand side 4, 6, 18, they can be of my B. So I can rewrite that equation which is Ax equal to B, and once I know, then I can have different feasible solutions from those. There are n number of set 1 solution, set 2 solution, set 3 solution, and 4, 5, 6, 7. We'll get enormous different variety of solutions. Sometimes it is possible, sometimes it is singular, sometimes it is non-singular, and so and so. But once you get the values, for example, first case you got x4 equal to 0, x5 equal to 0, second x3 equal to 0, x5 equal to 0, third x3 equal to 0, x4 equal to 0, and then you arrive to different solutions from time to time. But out of those, you can also see to that because of the values, the variables, when x2 equal to 0, x2 equal to 0, or x3 equal to 0, or x4 equal to 0, the different solutions will behave in a different way. That means it is not guaranteed that all the time in all steps you get the solution from time to time. So what we do basically in a simplest method, we represent that minimization of the function, which is not simply x1 plus 2, x2 plus x3, but I can represent that in the form of C transpose of x. Okay, instead of saying x1, x2, x3, I can represent C transpose of x with a constraint which is x equal to b as well as x greater than or equal to 0. Okay, and then probably if there are many variables, so then I can write minimize the function. Okay, the first function, second function, you can keep on adding, and subject to different constraints that need to be solved. So let's imagine that I have n number of power plant, and the cost characteristic of each power plant is linear. I have to optimize the total cost of the system. So then I have to add many linear functions that need to be optimized with constraints such as P max, P mean, etc. Now the simplex method, which is, as you all know, so xb, if you like to get a variable of xb, which is b inverse small b minus b inverse n of xn, and similarly z also can be derived from this. So the problem here, where the lambda is a vector, which is ideally the dual variable vector, and that also need to be determined. So if you continue further, you could see that the solution can be obtained in a long run, and we can define different variables in those linear expressions. Now, from one of the important variable in case of linear optimization is pivoting, and probably you can add pivoting variables in a particular row to handle such challenges. So simplex mechanism, it talks about different conditions, like whether the variables are positive or variables are negative, and you can understand the different steps actually to solve this linear programming. I'm not really getting into detail, but I'm just touching upon the exterior to make you understand what linear programming is all about due to sort of time. And this is what the simplest code that people used to follow. So first of all, you get a basic feasible solutions and find out if the current solution is a maximizer, and if all DJs are less than 0, then you stop. Otherwise, you continue to the next step and find out which non-basic variable enters the basics of x and j. Most positive one is dj, and find out which variable xbi leaves the basis that is minimum of bi upon yij, yij greater than or equal to 0, and then develop the new basic and get a new basic feasible solution, and then repeat, go to step number 2 and keep on repeating till you land up with a final solution. So this is how it works actually graphically. So you have an initial point, and then you move to a first jump, all right, and then you move to a second jump, and then the last jump, and then finally you get a solution that you have proved graphically. Now this can happen your mathematical way also. There are different linear programming features, and so what I wanted to highlight here, all are requested to get into the LP tool of MATLAB, where any linear optimization problem can be solved. And you can also use different textbooks to understand more about linear programming. And this is not necessarily part of this program, but at least we believe that the power engineers, before they get into different concept of optimization, this must carry the basics of linear programming as well as nonlinear programming with equality and inequality constraints. So with this note, thank you very much.